Something passed through our solar system in 2025 that was born around a completely different star, potentially in a very different part of the Milky Way, long before our own sun existed. And the James Webb Space Telescope didn't simply take pictures of it. Webb analyzed the light coming from the material surrounding it, allowing scientists to identify molecules and investigate the chemistry of a comet that formed outside our solar system. For the first time, astronomers had an extraordinary opportunity to study material from another planetary system without sending a spacecraft across interstellar space. The object had come to us. And what scientists discovered about its chemistry was unlike anything previously measured in our own family of comets. The story began on July 1, 2025, when the ATLAS survey in Chile detected a faint moving object. ATLAS, short for Asteroid Terrestrial Impact Last Alert System, is designed to search the sky for objects that could potentially pose a danger to Earth. But this object wasn't an incoming threat. Its orbit revealed something much more unusual. It was moving along a hyperbolic trajectory, meaning it wasn't gravitationally bound to the Sun. Instead of orbiting our star like a normal solar system comet, it was passing through and would eventually leave again. The object was designated 3I, Atlas, making it only the third confirmed interstellar object ever observed passing through our solar system. The first was Oumuamua, discovered in 2017. Its unusual shape and behavior sparked years of debate. The second was 2I, Borisov, discovered in 2019. Borisov behaved much more like a conventional comet, producing gas and dust, but it was faint and scientists had limited time to study it. Then 3I, ATLAS arrived. This time, astronomers had something previous discoveries hadn't provided: advance warning and enough brightness to organize an enormous international observing campaign. Hubble observed it. Webb observed it. ALMA observed it. Ground-based observatories in Chile tracked it. Spacecraft and telescopes around the world followed its journey. That made 3I, ATLAS an unprecedented scientific opportunity. When it was discovered, the comet was already moving extraordinarily fast, traveling through the inner solar system on an escape trajectory. It was heading toward the Sun, but its orbit ensured that it would never become a permanent member of our planetary system. Hubble observations helped scientists estimate the size of its solid nucleus, although the exact dimensions remained uncertain because the surrounding coma made direct measurements difficult. As sunlight warmed the object, frozen material began escaping from its surface and interior. Gas and dust surrounded the nucleus, creating the familiar coma of an active comet. Its closest approach to the Sun occurred on October 30, 2025, at a distance of roughly 1.36 astronomical units. That meant it never came close to Earth's orbit. There was no impact threat. But scientifically, it was incredibly valuable. Oumuamua had provided very little opportunity for detailed chemical analysis. Borisov gave scientists much more information, but 3I, ATLAS was observed with an even broader collection of instruments. And then the measurements started arriving. One of the early breakthroughs came from observations of water production. Scientists detected hydroxyl, a chemical product created when sunlight breaks apart water molecules. That provided evidence that water was actively escaping from the interstellar comet. But detecting water was only the beginning. The real scientific prize was discovering what that water could reveal about the comet's birthplace. Water contains hydrogen, and hydrogen exists in different isotopic forms. One of these is deuterium, often called heavy hydrogen, which contains a proton and a neutron. The ratio between deuterium and ordinary hydrogen can preserve information about the environment in which water formed. In extremely cold regions, chemical processes can produce very different isotope ratios than those found in warmer environments. That means a comet's water can act like a chemical time capsule. When researchers examined 3I, Atlas, they found an unusually high deuterium to hydrogen ratio compared with typical solar system comets. The results suggested that the environment where this comet formed was significantly different from the region that produced many of the comets we know from our own solar system. This is important because comets preserve material from the earliest stages of planetary formation. They are essentially frozen leftovers from the construction of planetary systems. And 3I, ATLAS appeared to be carrying leftovers from a system we could never otherwise visit. Then came observations from the James Webb Space Telescope. Webb's MIRI instrument observes infrared light, allowing astronomers to identify chemical fingerprints in the gases surrounding distant objects. Instead of simply seeing a bright spot, Webb could separate the infrared light into individual wavelengths. Each molecule interacts with light in its own characteristic way. Water produces one pattern. Carbon dioxide produces another. Methane produces another. And those fingerprints allow scientists to determine what is actually present in the comet's coma. Webb observations of 3I, ATLAS revealed water vapor, carbon dioxide, and methane. The methane detection was particularly important because methane is highly volatile and behaves differently from water ice. Its presence, combined with the other measurements, provided another clue about the conditions under which this comet formed. Scientists also studied where the different gases were appearing around the nucleus. Water was distributed broadly throughout the coma, while other molecules were more concentrated closer to the nucleus. That difference can reveal how various ices are stored inside a comet and how they escape when sunlight heats the object. In other words, astronomers weren't simply asking, what chemicals are here? They were asking, where are those chemicals coming from? And that distinction matters. A comet traveling through interstellar space for millions or even billions of years can develop a radiation-processed outer layer. Cosmic radiation gradually alters the surface material. But deeper beneath that altered exterior, ancient material can remain protected. When the comet approaches a star and its interior begins warming, gases trapped beneath the surface can escape. That gives scientists a chance to examine material that may have remained largely untouched since the comet formed. Other observatories studied the isotopes of carbon and nitrogen in 3I, Atlas. Isotopes are different versions of the same element, and their relative abundances can preserve information about the chemical and physical environment where material formed. The measurements from 3I, ATLAS showed unusual isotope ratios compared with many comets from our solar system. Taken together with the unusual deuterium abundance, methane, carbon dioxide, and other chemical measurements, the evidence pointed toward a formation environment very different from the one that produced our familiar solar system comets. Scientists have considered the possibility that its parent star was older than the Sun or formed in a chemically different region of the Milky Way. But there is an important distinction here. Astronomers can use chemistry and orbital dynamics to constrain the comet's history, but they cannot simply look at 3I, ATLAS and identify its exact parent star. Its birthplace remains unknown. What they can say is that the chemistry carries information about an environment unlike the one represented by most comets we have studied close to home. That is the real significance of 3I, Atlas. It gives scientists a sample of another planetary system without physically traveling there. Imagine trying to send a spacecraft to another star. Even our fastest spacecraft would require enormous amounts of time to cross interstellar distances. Yet nature occasionally does something extraordinary. It throws material from another planetary system directly into our cosmic neighborhood. For a few months, humanity can point its telescopes at that material and read the information encoded in its light. Then the visitor disappears again. 3I, ATLAS passed the Sun, continued outward, and began its journey back into interstellar space. The observing window was temporary. Every spectrum had to be collected while the comet was bright enough, active enough, and close enough for our instruments to detect. That makes every successful measurement incredibly valuable. The discovery also changes how scientists think about comet diversity. For decades, most of what we knew about comets came from objects born around our own sun. Naturally, we used those comets as examples of what comet chemistry should look like. But 3 interstellar objects have now shown us something important. Our solar system may not represent the full range of planetary systems across the galaxy.